Please.
Thank you. It's a pleasure to be here. I would like to thank the organizers for inviting me to give a talk here. So before I talk about equations of modular curves, I would like to tell you a little bit about what are modular curves and why am I interested in their equations. So our story starts with just trying to solve equations. So my interest lies in solving equations in rational numbers or integers. These kind of equations are called Diophantine. Maybe the earliest attempt recorded of trying to do such a thing is the famous equation of x squared plus y squared equals z squared, which by now we do know how to solve. And quite more generally, Diophantus 2000 years ago researched the question about arbitrary quadratic. And we also know how to solve that one. He already did. And on the bottom left of the screen, you can see the way he did that, basically by rational parameterization. So you take 1 point on the circle, or more generally on the conic representing this equation, and you pass a line through a rational slope, and you hit another point of the circle, and this way you get a rational parameterization of a point of the circle, and you get all possible solutions. But then you consider, okay, what's the next step? Let's try to consider an equation of the form y squared equals a cubic in x. And this equation, for reasons that I will explain in a minute, is called an elliptic curve. And you can see its shape right here. And this is a more complicated question, which until now we are attempting to solve in various ways. So what are those elliptic curves? Maybe the main breakthrough in understanding elliptic curves was when we tried to understand the complex solutions to this equation in the 18th century. And here you can see a famous theorem of Weierstrass saying that every set of solutions to such an equation over the complex numbers can be achieved in the following way. We take a lattice. You see here a picture of a lattice in the complex numbers. And we mod out the complex number, we quotient them by this lattice. That is, we take this parallelogram and we identify opposite edges. So if you identify a pair of opposite edges, you get a cylinder. And when you identify the other end of the other pair of opposite edges, you get this torus, this donut-shaped thing. And what Weierstrass understood is that every elliptic curve can be constructed as this donut, and vice versa. And the nice thing that we get from that is that over the complex numbers, we have naturally an addition operation. And since the lattice is closed under addition, this gives us an addition operation on the quotient, which means that we have an addition law on our elliptic curve. And on the bottom right corner of the screen, you can see a geometric description of this addition law. So if we take 2 points on the curve and we connect them by a line, then it intersects the curve at a third point. We reflect that point in the x-axis and we obtain the sum of these points. Why is this description so important? Well, now the next slide will be full of formulas, but the exact formulas don't really matter. The idea is that if we have 2 points, we can obtain a formula for their sum, which consists of only basic operations, field operations, addition, multiplication, subtraction, and division. So if we start with 2 points whose coordinates are rational, their sum is also rational. Another consequence is the fact that this addition is commutative. It doesn't matter in which order we add the points, which could be seen already from the description over the complex numbers. So, and maybe one thing I should add, in order for this addition to really form the structure of an abelian group, we need a zero element, which we construct by adding a point at infinity. And if we have 2 points, for example, if you see here in the picture, you have 2 points q and minus q that lie on a vertical line, then there's some, we define it simply to be that point at infinity. So to obtain the minus of a point, we just reflect it in the x-axis. You can also see here that the generate case where we add a point to itself, taking the tangent to the elliptic curve. So we have an addition operation on solutions to our equation. This addition operation is commutative and it forms the structure of an abelian group on the points with rational coordinates. Here's an example for points not with rational coordinates, but for the addition operation. So if we look at the curve y squared equals x cubed plus x, and we look at the following 3 points, 0, 0, I0, and minus I0, then each of them is a point of order 2. If we add it to itself, we obtain 0. Okay, that's because their y coordinate is 0. So when we reflect them in the x-axis, we obtain the same point. Similarly, if we look at the curve y squared equals x cubed minus 1, again, we have 3 roots of this polynomial, and each of these 3 roots give us a point of order 2. Okay, so now that we have an abelian group, the next important result that was obtained for understanding the structure of elliptic curves is that this abelian group is finitely generated. The reason that this is so important is because we really understand very well the structure of finitely generated abelian groups. That is, we have a theorem that classifies all such abelian groups. So we have a rank and some torsion part of this abelian group. And that's what we want to understand in general, to understand the structure of the abelian group. So in this talk, we will focus on the torsion part of this abelian group, even though the question of rank is a highly interesting one. So maybe I will start by saying that just computing the torsion for a specific elliptic curve is not too difficult. So we have a theorem, the Nagel-Lutz theorem from 1937 already, that if we have a point of finite order with rational coordinates, then the coordinates are actually integers. And moreover, we can even restrict the y coordinate to either y equals 0, as we saw before, for points of order 2, or y squared divides some number called the discriminant of f. But I will not go into details of that. But a larger question naturally follows. So what points of finite order can occur at all? And this was answered by Maser much later in 1977 in a theorem that states that if we have irrational points of finite order, then this finite order could be at most 12. And in fact, he even classified which possible torsion subgroups can appear. But in order to understand better this result, to say something about its proof, or to generalize it, we need to expand our realm a little and understand more about torsion points, not only over the rational numbers. So for this, we will introduce the notion of an algebraic number. So we will call a number algebraic if it satisfies a polynomial with coefficients that are rational. So for example, I is an algebraic number. It satisfies the polynomial x squared plus 1. Square root of 2 is algebraic. It satisfies the polynomial x squared minus 2. And roots of unity are algebraic. They satisfy the polynomial x to the n minus 1. On the other hand, numbers like pi or e are not algebraic. And we will use the following theorem. The algebraic numbers form a field, and we will denote it by q bar. We will also need the notion of an automorphism. So an automorphism of the algebraic numbers is just a map that, well, an invertible map that preserves the field operation, the addition and the multiplication. Here's an example. So first of all, maybe note that if we have a rational number, then any automorphism of the algebraic numbers fixes that number. One can start by looking at 1, then extending to positive integers, then to integers, then to rationals. But more importantly, suppose we look at I. We want to see what sigma does to I. So we know that sigma I squared, because sigma preserves multiplication, is the same as sigma of minus 1, which is minus 1. So sigma I must be one of the roots of minus 1, either plus or minus I. And quite more generally, if we have some algebraic number, then sigma takes it to one of its conjugates, one of the other roots of the same irreducible polynomial. So all these automorphisms form a group by composition, which is called the absolute Galois group of the rational field Q. And this group acts on solutions to our equation. So if we have an elliptic curve and we look at points with coordinates which are algebraic numbers, then by acting with an automorphism on these coordinates, since these automorphisms preserve the multiplication and addition, they also preserve the equation of the elliptic curve, and we obtain another point, which is a solution to our curve, to our equation. Okay, now we would like to look again at torsion points on our elliptic curve, but this time with coordinates in the algebraic numbers. So before we do that, we have to understand the torsion points over the complex numbers. So on the right-hand side, you can see a lattice in the complex numbers, and we can see the torsion points of order 5 in the quotient. So each point of the 25 points you see here, if we multiply it by 5, we obtain a point of the lattice, which means that in the quotient, it's a torsion point of order 5. So it's a point of finite order. Okay. In general, if we look at the torsion points over the complex numbers, then these are exactly the points that if we multiply them by a number n, we land in the lattice, which means that this is simply dividing the lattice by n. So we always get this structure of a square grid of n by n points, which as an abelian group has the structure of z mod nz cross z mod nz. So here's an example. If we have some lattice of the form z plus tau z, where tau is some complex number, then the two torsion points will have the structure of z mod 2 cross z mod 2. And they will just be given by 0, half, tau over 2, and 1 plus tau over 2. These are all the half points of the lattice. Okay, now we want, inside these points, we want to understand the points with algebraic with coordinates that are algebraic numbers. So for that, we recall the formulas that we had for addition of points, and recall that they were all given by rational functions. And now we can look at the map that sends a point to its multiple by n. So that's just composing addition of a point with itself n times, and that gives us another rational function with polynomials. So all these symbols here, phi n, omega n, psi n, are just polynomials in x and y. And the main reason that is important is because in order for a point to be a torsion point of order n, a point of finite order n, we just need this to vanish. So we need n times the point xy to be the 0 point. So obtaining the 0 point is the same as having these denominators here vanish. So it's a polynomial condition on x and y. We just want psi of n to be 0. And the nice thing is that we can translate it to a polynomial condition only on x. And let's look at a very simple example, the example of 2 torsion. So suppose we have a point which is a 2 torsion, then we already saw before that it means that the y coordinate is 0. And because y squared equals f of x, where f of x is the cubic, then y equals 0 is the same as f of x equals to 0. So we get a polynomial condition only on x. So that means that to be a torsion point, x must satisfy some polynomial with rational coefficients, which means that all our torsion points are algebraic. And as a corollary, we see that we have an action of the Galois group, of the absolute Galois group, on our torsion points. Because since automorphisms preserve all the field operations, they also preserve the multiplication by n map on our elliptic curve. So if we start with a point which is of order n and act with an automorphism, we obtain another point of order n. And since we started with a point which was algebraic, we can act with an automorphism of the algebraic numbers and obtain another point with algebraic coordinates. Okay, so now we have those points of finite order of our elliptic curve, which are all algebraic numbers over the rationals, and we have an action of the Galois group. Here's an example. So remember y squared equals x cubed plus x from before. Then the 2 torsion points, we have 4 of them. Remember, this is 2 by 2 square grid. And these are simply 0, the point at infinity, and the 3 roots of this polynomial, I, minus I, and 0, with y coordinate 0. Now, if we have an automorphism of the algebraic numbers, an element of the Galois group, then it either sends I to itself or to minus I, and it fixes 0. So if it sends I to itself, it fixes all the points here. And if it sends I to minus I, then it will interchange the 2 points I0 and minus I0. So that's the action that we see on the torsion points. Okay, now this action gives us a representation of our Galois group. So we have a map sending a point to another point, using this for any automorphism, sending the point P to the point sigma of P. And we know that the torsion points of order n are of the form z mod n times z mod n. So every automorphism, every invertible map on this group will be a matrix, an invertible 2 by 2 matrix with coordinates in z mod nz. So this gives us a map from automorphisms, elements of the absolute Galois group, to matrices, 2 by 2 matrices. So to be more explicit, let's see an example. Again, we continue with the example from before. So we have these two torsions of our elliptic curve, two torsion points. So there is an isomorphism between these torsion points with the group Z mod 2 cross Z mod 2. And we will identify it by sending the point I0 to the basis vector, to the first basis vector, and minus I0 to the second basis vector. So now what we said before, that if sigma sends I to minus I, then it swaps these two vectors. So the resulting matrix that we will get is simply the matrix that swaps the two basis elements. So this is the matrix you see here, 0, 1, 1, 0 in GL2 of Z mod 2Z. So we get a map that associates to every element of the absolute Galois group a matrix. And this map is compatible with composition, which gives us a representation of our Galois group. Okay. So what can we say about this representation? For example, can we get all matrices in this way? Can we permute the torsion points in any way we like? Or can we only obtain certain operations? So for example, in the example that we saw before, we have only two possibilities, right? Either sigma fixes everything or it swaps the two basis elements. So it's true that in this situation, the entire group is not very large because this is GL2 of Z mod 2, it has only 6 elements. But we see that the image of our representation consists of only 2 of these matrices out of the 6. And more generally, if you look at this curve and you will look at other torsion points of finite order, you will see always that the image of the Galois representation, meaning the matrices that we can actually obtain this way, is relatively small inside our our group of matrices, or of possible matrices. So the reason that this happens is because this is a very special kind of curve. This is a curve that has something called complex multiplication. So complex multiplication, very simply, just means that there is some complex numbers. Remember that our elliptic curve was a quotient of the complex numbers by a lattice. So there is some complex number that preserves the lattice. So for example, if we have the lattice Z plus IZ, it has complex multiplication by I, because multiplication by I of this lattice is the same lattice. And this corresponds to the curve y squared equals x cubed minus some constant times x. And the map that we obtain on the level of the algebraic curve is the map sending the point xy to the point minus x iy. So that's an automorphism of the curve, which comes from this complex multiplication. And similarly, if we have the third root of unity, it has complex multiplication by third root of unity. That's because zeta squared plus zeta plus 1 is 0. And this corresponds to a curve of the form y squared equals x cubed minus d. And in this case, the map is simply multiplying x by third root of unity. So in these situations, because we have this complex multiplication, that forces our image to be small. So the automorphism that acts on our torsion points has to commute with this operation of complex multiplication, and that forces a condition on our image. So we only can take matrices which commute with this element, and that keeps our image quite small. So from now on, we will just ignore this case, leave it aside. And Serre in 1972 was able to obtain the following result So if we have an elliptic curve which doesn't have any complex multiplication, the size of the image of our Galois representation is very large. What is very large? So it's almost always everything. This representation is almost always surjective, covers all of GL2, all of the possible 2x2 matrices. But more generally, its index, the number of cosets it has in the larger group of 2x2 matrices, is bounded by a constant. I will now state some results which are stated in terms of a prime P, but you can interchange the results between primes and arbitrary positive integers, basically using Chinese remainder theorem. So this open image theorem led to a question which is now known as Serre's uniformity conjecture, that this bound, so maybe I will explain a little more. So Serre's result say that we have a bound on the index of these representations, the images of these representations, and this bound does not depend on the order of the torsion point. So it does not depend on prime P here. It only depends on the elliptic curve. And the conjecture is that it does not even depend on the elliptic curve. So when you go over all elliptic curves, it's almost always surjective, and in the few cases that it is not, you can bound the index. And the way that Serre approached this problem was by studying the maximal subgroups of GL2 Z mod PZ. So the idea was, we will look at all the elliptic curves such that the image of our representation is contained in one of the maximal subgroups. We will see that there are no such elliptic curves defined over the rational numbers, or we will classify the specific cases in which there are elliptic curves defined over the rationals. And that will leave us only with the case that the image is everything. So for that, we classify the maximal subgroups of GL2 Z mod PZ. There are several types. The first type is Borel subgroups. These are those that stabilize a line. We have split cartons. These are groups of the form of diagonal matrices. And we look at its normalizers. And we have what is called a non-split carton. So if we pick U to be a non-square in Z mod PZ, then we can take matrices of the form A, U, B, B, A. This is basically the image of the multiplicative group of the field with P squared elements. And this, when we take the normalizer of this group, we get another maximal subgroup of GL2 Z mod PZ, and all maximal subgroups are conjugate to one of these. Oh, sorry, and I forgot, in some cases there are exceptional subgroups. These are finite groups, specific finite groups that can appear as maximal subgroups in several cases. Okay, so now, in order to consider all the elliptic curves in general, or all the elliptic curves whose image of the Galois representation is contained in a Borel subgroup or in the normalizer of a split carton, I have to introduce some notion of talking about all elliptic curves in a uniform way. And for that, we introduce the notion of a moduli space for these elliptic curves. So we start by looking at the upper half plane. So the upper half plane, all the points in the complex plane which have imaginary part, which have positive imaginary part. So for each such point, we can associate a lattice. The lattice built by Z plus tau Z. And this lattice gives us an elliptic curve by quotienting by that lattice. So if we have, moreover, if we have some lattice in the complex number, there's always some such number in the upper half plane such that our elliptic curve is isomorphic to this elliptic curve made from that point tau. Moreover, we have an action of the group SL2Z, group of 2x2 matrices with integer entries, by Möbius transformation. And this action is compatible with construction of these lattices. So these give the same lattice. And we can see that two elliptic curves that we construct in this way are the same if and only if there is some matrix with 2x2 matrix with integral entries that sends one tau to the other. The point of this is that if we look at the quotient space, taking the upper half plane and quotienting it by the action of SL2Z, we obtain exactly the elliptic curves up to isomorphism. So we have a bijection between this quotient space, SL2Z mod H, and the elliptic curves over C up to isomorphism that is obtained by taking a point to the lattice, to the quotient by that lattice. And we can do more. So if we have some subgroup, some discrete subgroup of SL2Z, we can quotient H by that subgroup. We will obtain something larger, and it will it will give us a and it will give us in general some moduli space, which I will describe shortly. The problem with this thing, this moduli space, or maybe the first problem, is that it's not compact. So when we do geometry, it's much easier to work with compact things. So we compactify it. We add some points. We add the point at infinity. We add all the points on the real axis, and we identify them up to the action of our group gamma. So on the bottom right-hand side, you can see the quotient space SL2Z mod H, that's in the striped area here. So this is a fundamental domain for the action of SL2Z on this upper half plane. So every point has a point in this domain. And to compactify it, we can simply add the point at infinity. Now, the S and T that you see here are the two generators of the group SL2Z. And if we have some subgroup gamma of SL2Z, we can describe it in terms of generators and relations, and we can see what its cosets are in SL2Z, and this gives us a way to build its fundamental domain. For example, by taking this fundamental domain and acting with S, we obtain the part that is labeled by S in this picture. And if we operate by T, we obtain the part that is labeled by T in this picture. So this gives us the non-compact part. And to compactify it, we want to add points on the real axis and at infinity. Now, if we just added these points with the complex topology, our quotient wouldn't be Hausdorff. There would be too many points in the neighborhood of each such point. So to get a really nice space, what we do is that you can see on the bottom left side of the screen. We have for the point of infinity, we add neighborhoods of the form, all the points which have imaginary part large enough. So the larger your imaginary part is, the closer you are to infinity. And we translate those neighborhoods to neighborhoods of points on the real axis by acting with appropriate matrices of SL2Z. of our discrete subgroup. And we only take points which have rational coordinates. So points that belong to the real axis which have rational coordinates. So this creates a very nice geometric structure. Basically, this is a curve over the over the complex numbers, and it's a compact curve, which means it's a Riemann surface. And locally, every point has a neighborhood that looks like the complex numbers. Now, for that to actually have the complex properties that we want for complex analysis, we need to have local coordinates at each point that will be compatible. And here you can see the description of how we build local coordinates at a cusp at one of these points that we added to compactify our curve. So on the left-hand side, you can see our cusp in which all those different stripes are identified. So first we use a 2x2 matrix to stratify all those stripes. That was you see on the top. And then we use the map e to the 2 pi I to convert these stripes into a circle. So basically we have a local coordinate map, which is of the form e to the 2 pi I tau over h, where h is the width of this stripe. Specifically, if our point is the point at infinity, and we have this matrix 1, 1, 0, 1 in our group, then the local coordinate is simply e to the 2 pi I tau. So for the case of the entire SL2Z, this is just the local coordinate at infinity is given by e to the 2 pi I tau. Okay, but what in general does this moduli space describes? So if we have some subgroup of GL2Z mod NZ, and we have an isomorphism between our points of finite order n and the group Z mod n cross Z mod n, then we can look at pairs, an elliptic curve and such an isomorphism, and identify them when this diagram commutes. So when the isomorphisms are compatible by the action of an element H, which belongs to our subgroup. So when we identify the torsion points of each of the elliptic curves with this group, Z mod n cross Z mod n, then we want to have an element of our subgroup that will be the matrix coming from this isomorphism. And we can form the moduli space of all those pairs modulo this equivalence relation. And this moduli space has an action by the Galois group simply by acting on the elliptic curve and on this isomorphism. And by unfolding the definition, we can see that a point in this moduli space is rational if and only if the elliptic curve is rational and the image of the Galois representation is contained in this subgroup H. Now this moduli space is precisely, if we complexify it, we obtain its complex points are precisely the quotient of the upper half plane by the subgroup corresponding to this H. So we can look at all the points, all the matrices, all the 2x2 matrices, which modulo n, their coordinates live in H. Here are some examples for subgroups that are used frequently. So first, there's gamma n. This is the principal congruent subgroup. So these are all matrices, 2x2 matrices with integer entries, that if we take their residue when dividing by n, taking the modulo n, we get the identity. Now, any group that contains such a principal subgroup is called a congruent subgroup, and all the subgroups that we will consider will be of this type. So we have a subgroup corresponding to the Borel. So remember, the Borel was the maximal subgroup of GL2 Z mod PZ or Z mod NZ that stabilizes a line. So we can take all the 2x2 matrices that if we reduce the mod n, we obtain a matrix in the Borel subgroup. These are the groups gamma 0 of n. And similarly, we can obtain groups for the Cartan and non-split Cartan and their normalizers. Okay, so now we have moduli spaces, which are compact Riemann surfaces that classify all the elliptic curves such that the image of their Galois representation lies in a certain subgroup. So that returns us to Serre's uniformity conjecture. So stated differently, a theorem of Serre concerning from the same paper concerning the exceptional case. So suppose that that P is prime greater than 13, and we have a subgroup that is contained in one of the exceptional subgroups. Then the modular curve corresponding to this subgroup has no rational points, which means that there are no elliptic curves defined over the rationals for which the image of the Galois representation is contained in the exceptional subgroup. Then there's the theorem of Mazur, that for P greater than 37, the modular curve x naught of P, so this is the modular curve corresponding to the Borel subgroup at P, has no non-CM, non-cuspidal rational points. So here I should explain why do we look for non-CM, non-cuspidal points. So remember that our moduli space classified elliptic curves, and then we added cusps. We added cuspidal points to make it compact. So the cusps don't really correspond to elliptic curves. They correspond to a degenerate case of elliptic curves. So we don't really care about those when you want to state something about all the elliptic curves. And non-CM, that if you remember was already in the in the previous time we talked about Serre's uniformity conjecture. So when the elliptic curve has complex multiplication, the image of the Galois representation is small. So we don't want to look at these points. So saying that the modular curve has no non-CM, non-cuspidal rational points means that there are no elliptic curves defined over the rational with no complex multiplication such that the image of the Galois representation is contained in the Borel subgroup. This specific theorem is the reason that one can classify and bound the order of a finite or of a point of finite order on an elliptic curve. So this is the statement of Mazur that we had in the beginning of our theorem. Okay. Now, in 2013, Bilou, Perot, and Reboledo showed that the modular curve corresponding to the split Cartan, to the normalizer of the split Cartan, has no non-CM, non-cuspidal rational points. So now we know that if we have an elliptic curve, that the Galois representation is not surjective, and P is large enough, it is not contained in a Borel subgroup by Mazur. It is not contained in an exceptional subgroup by Serre. It is not contained in the normalizer of a split Cartan by Bilou, Perot, and Reboledo. So it must be contained in the normalizer of a non-split Cartan, which is the only other maximal subgroup. So Serre's uniformity conjecture is reduced to saying that the only rational points of the modular curve corresponding to the normalizer of the non-split Cartan are the points with complex multiplication. The only elliptic curves that that have their image inside the normalizer of a non-split Cartan are elliptic curves with complex multiplication. So what do we know about this conjecture? So note that the conjecture is for P greater than 11. So we know it for P equals 13. That's the largest prime for which we know that it holds. And we know it since last year, 2 years ago now. That is that the modular curve has exactly 7 rational points, all of which are complex multiplication. For the next 3 primes, we only know that there are no small rational points on this curve. Small meaning we search in a box. we bound the numerator and denominator of the entries, the coordinates of these points. And we've seen that there are no such points. I should remark also that for such curves which have low genus, there are heuristics that say that we should expect, if there are rational points, their coordinates should be small. So it really enforces our belief that there are no rational points there, but we don't know how to prove it yet, other than the complex multiplication points. Now, both of these theorems rely on explicit equations for the curve. Specifically, the result you see for 13 comes from the fact that Bar-Ilan in 2014 was able to obtain an explicit equation for this curve. And then one can use methods for finding rational points on curves given their equation. So this is the reason that we're interested, or one of the reasons that we're interested in equations for modular curves. So the idea is that we would like to produce equations for modular curves for arbitrary primes and be able to search for points, and be able to use our methods that work with explicit equations. So also in the cases that you see here for 17, 19, and 23, Mercury and Schoof obtained explicit equations for these curves to be able to search for rational points on them. Okay, so the way we continue to understand how to obtain equations for this modular curve is by looking at something called differential form. So our idea will be to use differential forms to get nice coordinates for our curve and get equations from that. So what is a differential form? So a meromorphic differential form on a curve is simply something that you can integrate. So it's something that locally looks like fq dq, where q is a local coordinate, and fq is some Lorentz series. If this Lorentz series at a certain point is a power series, then we say that it's holomorphic there. And here are some examples. So for example, if you look at complex plane, just something like q squared plus 2q minus 3dq is a holomorphic differential one form. Let's move to something nicer, so a compact Riemann surface. For example, the simplest case is the Riemann sphere. So you could say, okay, look at something of the form q dq. So this looks like a nice one form, and it is a meromorphic differential one form, but it's not holomorphic, because if q is a local coordinate at point 0, then looking at its inverse and just looking at the local coordinate in infinity, we see that we have a pole there. Here's an example that is more related to our case. So I'm not saying what gamma is yet, but we're looking at some modular curve x gamma. And we look at the function, so we let R4 of n be the number of ways to represent n as a sum of 4 squares. And we look at the function θ4 of tau, which is a power series whose coefficients are these R4 of n, these numbers of representations of q to the n, where q is our local coordinate at infinity. And we form the differential one form, θ4 tau d tau. So this is holomorphic for any tau in the upper half plane. And it has a simple pole at infinity just by looking at these local coordinate. Now, in order for this to make sense, I should say that omega is really defined on our modular curve. So maybe in this last example, so if we have some gamma in our subgroup gamma, then 2 points tau and gamma tau are the same point, are identified in our moduli space. So for this differential to be well defined, we must have it invariant under gamma. So substituting that tau or gamma tau should be the same. So in this case, this holds for a certain subgroup, gamma 0, 4, all the 2 by 2 matrices whose bottom left entry is divisible by 4. That is, all the 2 by 2 matrices that if we reduce them by 4, we're in the Borel subgroup corresponding to 4. So we note that this compatibility condition obtains the form theta 4 of gamma tau is c tau plus d squared, theta 4 of tau for any gamma in our group. This is sometimes the more standard way to define modular forms by satisfying this kind of condition. But for us, our definition of a modular form will simply be a meromorphic one form, which is holomorphic away from the cusps, and at the cusp it has its most simple pose. This geometric formulation is more compatible with our needs. So if it is holomorphic everywhere, also at the cusps, it is called a cusp form. So in the example that we just saw, this omega, which came from theta 4, is a modular form for the group gamma 0 of 4. And in general, we denote by M2 of gamma the space of modular forms for gamma, and by S2 of gamma the space of cusp forms, the holomorphic differentials. So what we saw earlier was that theta 4 is in this space of modular forms for gamma 0 of 4, and maybe one of the famous applications of modular forms is using the fact that these are spaces that we can calculate their dimensions very easily because they're basically geometric. So in this case, we know that this space has dimension 2, and we can explicitly construct, in this slide, you can see an explicit construction of functions that live in that space. And you see here 2 linearly independent functions. So theta 4 must be some linear combination of them. And a quick check by comparing Fourier coefficients, one can see that it is actually the bottom one. And this gives you an explicit formula for the number of representation of a number as a sum of 4 squares, which are just the coefficients here. This is already due to Jacobi. That's as an aside. So why do we care about these modular forms or differential one forms? So the holomorphic differential forms. So this is because of a theorem known as Petri's theorem, even though it's due to Nether, Enrique, Babbage, and many more mathematicians, which if we have a curve and we have a basis for the holomorphic differentials, then they give us a map into projective space. And if X is nice enough, then this map is injective. And moreover, there's an explicit description for the number of relations we expect to have of each degree. So in particular, if our curve is a modular curve of the form that we saw earlier, then a basis for the holomorphic differential is a basis for the space of cusp forms, the modular forms which are holomorphic everywhere, even at the cusps. The next thing we need is a result known as the Sturm bound, that in order to compare 2 modular forms, it's enough to compare their Fourier coefficients up to a certain bound. So these 2 results combine to give us a good strategy to obtain equations for our modular curve. So we can compute a basis for the space of modular forms with respect to our subgroup gamma, and then look for polynomial relations. So the basis would give us the map, and the polynomial relations will give us the equations that they satisfy. And we can check the polynomial relations by checking the Fourier coefficients up to the Sturm bound. Okay, so now suppose that we have a subgroup of GL2Z mod NZ and some positive integer L. Our problem of finding an equation reduces to finding the Q expansion of a basis for the space of cusp form up to a certain precision. So this is known for the Borel subgroup for gamma 0 of n, and well, gamma 1 of n are all the 2 by 2 matrices for which the diagonal is also congruent to 1. So they actually fix a point. Because these are the classical, the groups used in classical theory. So this was already done for them. But when we're interested in arbitrary modular curves, especially things like the non-split Cartan subgroup, then we need to be able to do that for that group as well. Now, there are some results in this direction. So for some subgroups, there's a theorem saying that the modular curve is defined over Q if the determinant is surjective, but you can find the space of cusp forms by looking at a larger space. You can look at the modular forms for the principal congruent subgroup with coefficients in a cyclotomic field. These have action of the group GL2Z mod NZ, and you can look at the subspace fixed by your subgroup, by G. So if you have some subgroup of GL2Z mod NZ, you can look at all the at the invariant subspace under this group G, and this will give you your modular form. This approach is used by Zewina to compute the action on Q expansions. So you have Q expansion in this larger space, you compute the action, and then you compute a basis. There are two problems with this approach. First, the space here for the principal congruent subgroup over the cyclotomic field is much larger than our group. For example, if one looks at the non-split Cartan, this is of the size of n squared roughly, and this is of the size of n cubed. And it uses also numerical approximation with large denominators. It's really difficult to be able to compute the action of one of the elements here, specifically 0, 1, 1, 0 on Q expansions. Okay, so our result is that one can do that by working explicitly with modular forms on your group. And this is done by using the theory of modular symbols specialized to this subgroup. And as a corollary, one can obtain equations for some modular curves, most of which were already known. For example, you can see here an equation for the modular curve of the exceptional group S4, and the result we showed earlier of Bar-Ilan for the non-split Cartan for 13. And we get similar results also for 17, 19, and 23. And as another corollary of this approach, since we are working directly with the group, we have also the composition of the Jacobian of this modular curve. And we could obtain, for example, a new result regarding the decomposition of the Jacobian of the non-split Cartan at p equals 97. And in particular, we've shown that it has no elliptic curve factor, which is expected to occur for all non-split Cartan modular curves. Well, that is our results. Thank you for your time. Are there any questions?
Thanks a lot. Are there any questions? Comments?
So what is the last, can you go back just one slide?
Yes, sure.
So you have dimensions,
I mean, the result is more explicit than that. We have specifically the
eigenvalues.
Polynomials and eigenvalues, yes.
How you compute eigenvalues?
So basically, I have the space of modular symbols for,
okay.
For this group, and I have the Hecke operators there. And by simple linear algebra, basically.
And you can, so in this case, you essentially identify the corresponding holomorphic forms, right? If you know. Yeah. And how far can your algorithm run, for just out of curiosity, for what primes? What is feasible?
So it runs roughly in the same speed you have for gamma 0 of n and gamma 1 of n. It means that probably, well, if you want to compute the entire decomposition like here, so you have d cubed plus dl log L, where L is the precision.
It says for how, I mean, without going to supercomputer, what kind of primes you can cover?
So it depends on some parameters, for example, the group that you're using, because it will affect the dimension of the space. But for example, in the non-split Cartan case, it should be able to go up to several thousands.
I see. Okay, great.
Any other questions or comments?
Maybe I should say that it is used right now to compute the decomposition of Jacobians of 50,000 subgroups.
Are there any perspectives for using this for Hilbert modular curves?
No, I mean, this method is quite limited in the sense that it will only work for classical modular curves. There are many things that are specific to this case. I mean, for Hilbert modular curves, there are many other complications. Mm-hmm. We can talk about it in a later time, maybe.
Okay, well, thanks very much again.